All right, so before we get into the new content, let's talk about homework for just a little bit today. We just had the test for, actually I should pull this up. We just had the test 4 deadline. I was trying to remember the stats off the top of my head last lecture, so let me actually pull them up this time. So we can get some exact numbers. I was just making them up. I think I got them a little off. For the very first time. So for most of you, Task 4 is behind us. I've said this before, but Task 4 is kind of a bit of a spike up. And at the very least, I'm careful the way I word this, in the very least, the amount of time it takes to complete it. And then Task 5 and 6 get quite a bit easier, and then I word it the wrong way anyway, a bit less time consuming. Task 5, and I'm starting to hear this confirmed from students already, Task 5 should be nothing. It should be absolutely a breeze after going through Task 4. If it went from Task 3 right to Task 5 would feel like a little bit jump up. But after getting through Task 4, Task 5 feels like nothing. The code you're asked to write isn't all that much, and you have the tests to help you out. So you can run your tests that you wrote from Task 4 to help you write the code for Task 5 to make sure that you have everything right. Going through the pain of Task 4 and making sure those test cases are looking good. Not always complete. I'm already seeing some students who have the bare minimum testing to get through Task 4, and then that catches up to them on Task 5 and 6 because you don't have a good test suite. You just have the bare minimum that got rid of my incorrect solutions. That's one case. Hopefully that doesn't apply to too many of you. But the other case is you wrote good tests for Task 4, crushed Task 4, and now on Task 5 and 6 you have good tests to help you write the code. And you get to feel the benefits of test-driven development. Having a test before writing the code makes writing the code so easy. So between less code and having tests, Task 5 should be pretty straightforward. Task 6 is very little code that you actually have to write, but the code is a bit trickier to write. So it'll be more of a little bit of a challenging programming task in that you have to sit down and think about how you're going to approach the problem. But once you figure out how to approach it, once you design your solution really well and understand what you need to do, actually writing the code is almost nothing. And again, you have the test to help you out while you're writing the code. Very little code to traverse the tree and generate your linked list. So it should be a bit of a breeze once you're through Task 4. Task 4 stats, 310, it's a little over 60% of the class did complete the Task 4 before the deadline this morning, before the actual deadline. So over 60% of the class done with Task 4 on time. Everything's great. Scroll down. 398 have made any submission to Task 4. So we're, in terms of percentage of the class who submitted and completed the task, is looking pretty good. We did all right. I mean, not great, not objectively great, but considering it's Task 4 and what Task 4 is, that ain't so bad. And then, of course, over 100 students never even submitted the task. So there's nothing I can do, not much I can do there. I can't blame the task on that one. But those are kind of the stats we're looking at. If you needed a recovery opportunity for Task 4, don't worry about it. I've said this before, but that's what recovery opportunities are there for, especially when we have a spike in difficulty like Task 4 is. You use the recovery opportunity, it's no big deal. If this is your first one, just some recovery opportunity logistics. They do happen automatically, at least on your end. I, this morning, manually entered over 100 deadline extensions. But you should be able to see your recovery opportunity usage in AutoLab in the stats category. You can see how many recovery opportunities you've used just to double check against what you believe you've used. Make sure that number agrees with you. If it doesn't, talk to me. We can talk it out and figure out what went wrong. And when you go to the Task 4 submission page, it should say last day to submit is the Wednesday after break. So if you needed a recovery opportunity for task 4, when I look at the schedule, when I plan out the schedule for a course, I look at spring break and just treat it as a complete void in the schedule, like it doesn't even exist. So the 1-week extension actually takes you to the other side of spring break. So according to the calendar, you get a 2-week extension for using the recovery opportunity on task 4, which kind of lined up by accident, but I'm glad it did, and I'll make it line up like that on purpose in the future, that task 4 recovery opportunity, the first one anyway, does give you a 2-week extension to give you time to kind of decompress and over break. You can say, what the hell is 116 doing to my life, and figure all that out. Hopefully get caught up over break. I treat spring break as a void because you should actually be taking a break over break. I want to encourage you to actually take a break. And one thing I always recommend this, and I do this myself, of course, I take my own advice, is when you are having trouble with a programming task or any really technical, something that takes a lot of brain power to figure out, whenever I'm struggling with something like that, and I get to the point where I'm just staring at my laptop screen and I'm making no progress at all, and I could stare at that screen for another hour and make no progress at all, what I do is I just go to sleep. If it's late at night, I just go to sleep for the night. If it's during the day, I'll just close my eyes, take a quick nap, or just take a break and go do something else for a while, something that doesn't really use my brain much. And then when I come back to it, when I either wake up or come back to it, it's usually immediately I see exactly what my next step is, what the next thing I have to do to make some progress on that project is. So I do recommend that if you're just making zero progress at all on any of your programming, just take a break. The best thing to do is walk away from it for a bit, and then come back with fresh eyes, with a fresh brain, well-rested mind, and then you'll make a much better progress after that. Things that seemed impossible before your break will seem trivial after your break. And that's how I get stuff done. I can't just brute force stare at something and hash it out. Just take breaks. Helps a lot. There's something else. And over break. So especially over break, I encourage you to do that. Take at least one day. Hopefully you can take the whole week. If you're caught up with the course and all your other courses, take the whole week like you're supposed to. But if you're using the break to catch up, take at least one day, at the bare minimum, where you don't think about school and your classes at all. Just completely step away. Definitely helps. I'll be doing the same thing. I might only get away with one day where I'm not processing things. I got to get tasks 7, 8, and 9 ready, plan the rest of the lectures for the semester, make some slides. I got all kinds of crap to do. I want to make sure I take at least one day over break where I'm not doing anything related to school at all. Not going to do anything. Hopefully I can get away with more than one day, but we'll see how it goes. The spring break being a void applies to everything else too. So task 5 actual deadline and task 6 expected deadline are both the Wednesday after break. It came up in the other lecture. It's in the schedule, so you should already know that, but it did come up in the other lecture, so I'll make sure I mention it in case somebody else has that question here. So with that, does anybody have any questions about homework stuff or anything else before we talk about binary search trees? Okay. Talk about binary search trees. So this is what a binary search tree is. I got one slide on what a binary search tree is, and we're going to talk about it for the rest of the lecture. So a binary search tree is a binary tree that satisfies these two properties. For each node in the tree, every value that comes before that node's value is in its left subtree, and every value that comes after that node's value is in its right subtree. If you satisfy those two properties, you got yourself a binary search tree. So in this tree, the root node 5, everything in the left subtree comes before 5, and everything in the right subtree comes after 5. These binary search trees are going to use comparators, so this tree assumes that I'm using the default sorting of integers. so I'm using an int increasing comparator. Last time we saw the int decreasing, which sorted in reverse order. This I'm going to use the standard comparator, which is going to be the less than operator, which sorts integers in increasing order. So for this specific tree with that comparator, everything to the left is less than, everything to the right is greater than, and this is true for every node in the tree. So for this node as well, everything to the left is less than 2, everything to the right is greater than 2, everything to the left is less than 8, everything to the right is greater than 8. If that's true for every single node in your tree, you got a binary search tree. And the one kind of caveat, which isn't incredibly important, at least for our discussions in 116, is how to handle ties. If I want to insert the same value into this tree multiple times, we have a decision to make. It's an implementation detail, so it's not specific to the concept of a binary search tree. We want to focus on the concept of what a binary search tree is, not any specific implementation. So it's up to the implementations to decide how to handle ties. In our examples, we're just not going to have, we're not going to add ties to a tree, so we're not going to worry about it. But we do have to write the code in a way that will handle them. So how are ties handled? Sometimes the implementation won't handle them at all. It just won't allow it. You see this in your key value stores. If you got a key value store built on a binary search tree, which isn't totally uncommon, then you're just not going to allow duplicates. So it depends on your specific application, what you want to do. For what it's worth, the code we're going to write is going to break ties to the right. But we have 3 choices: either don't allow ties, break ties to the left, or break ties to the right. In our implementation, we're going to break ties to the right. So if we were to insert a duplicate value into our tree, when we see the code, you'll see that it would break ties to the right. Again, doesn't matter too much. It's these first 2 points that really matter. Everything to the left is less than, everything to the right is greater than. Assuming, I'll usually say less than or greater than during this lecture, assuming that we have integers sorted in increasing order, just because it's easier than saying according to the comparator comes before in the fully sorted order. I'd rather just say less than. So just to get some brevity in the lecture, I'll say less than or greater than. But it could be based on any comparator. So that's a binary search tree. That's what a binary search tree is. Here's part of the code of our binary search tree. Just like our stacks, our linked lists, our queues, our sorting method, and our binary tree, we're going to take a generic type. So we can store any type of value in our binary search tree. And just like our sorting algorithm, we're also going to take a comparator so we can store any type in any order. In a binary search tree, ultimately what we're doing is storing our values in sorted order. That's what we're doing with this property of a binary search tree. So if we take a generic type and a comparator for that type, we write our binary search tree code one time ever, and then we can store any type with any ordering in this binary search tree using the same code. So that's what we want to do, just the same thing we did with insertion sort. And last week when we introduced comparators, now we're using a comparator, same style of comparator, but we're using it in a binary search tree. There's 2 methods that we're going to write. There are other methods that we could add. We could have a delete method. We're not going to see that in 116 though. These are the 2 methods we'll stick with: insert and find. This will be the bare minimum we need to talk about binary search trees, the concept. So insert, add a value to the binary search tree. Find, check if a value is in the binary search tree, and our find method is going to return a Boolean, as opposed to our linked list find, which did return a reference to the node containing the value. Our binary search tree code, we're more concerned with just is the value in the tree or not. So we're just going to return true or false. True, the value you're looking for is in this tree. False, the value you're looking for is not in this tree. This is how we'll use our method. I'm going to create a new binary search tree with an int increasing comparator. And here's the code for that. It's just like the int decreasing comparator, except I'm using less than instead of greater than. So I'm going to get the default sorting of sorting our integers in increasing order instead of decreasing order. So that's the only difference, but that we are going to get the default sorted order for integers by using less than instead of greater than right there. We call insert a bunch of times. We call find a couple times. Find of 7, we expect to return true. Find of 8, we expect true. Find of 3, we expect false. 3 is not in this tree. Then we'll do an in-order traversal on this tree. Okay, well, there's a lot of code on the next slide. So any questions on BSTs before we get into more of the details? And one big thing we're going to watch for with insert and find is we want these methods to be fast. We want these to be fast. So one of the big questions is, or at least should be, we got array lists and we saw a sorting method on array lists. We saw linked lists. We have another data structure. And we didn't do it, but we could sort linked lists. We could do insertion sort with a linked list by going through the linked list with our comparator, comparing each value until we find one where the comparator says this value doesn't come before the value you're inserting, and then insert at that location. We could do insertion sort with a linked list, pretty straightforward, similar to how we did the array list. And it would actually be a little more efficient, right? No, it wouldn't be more efficient, would it? I don't know. I don't want to think about it right now. But anyway, we already have ways of storing sorted values. Why do we need another one? Why are we even bothering with this? Let's just use an array list for everything. Well, the reason is going to be efficiency. This is going to be fast, and specifically when we're inserting a lot of values. So when we're inserting values and maintaining sorted order as we're inserting values, that's when we're going to want a binary search tree. That's when this is the most useful data structure. Let's look at how we're inserting. So inserting, I want to insert some value into the binary search tree. And when we insert, there's a big thing that we have to be careful of when we're inserting into a binary search tree is that we have to maintain the property of a binary search tree, where everything to the left is less than, everything to the right is greater than, or everything to the left comes before, everything to the right comes after, according to the comparator in fully sorted order. We need to maintain that when we insert. So we can't just insert the thing anywhere in this binary search tree. We have to find a specific spot where we can insert the value that's going to maintain that property. So that's what we want to do with this insert method. And for what it's worth, we're breaking ties to the right. So the first thing we're going to do when we're asked to insert something is if the binary search tree is empty, just insert this value at the root. There's not much work that we have to do, not much thinking we have to do with that one. If the tree is empty, there's only one spot to insert it. It's the root of the tree now. This is just like our stack and queue implementations. When we're working with these node-based data structures, often our methods are going to have an if null. We're going to have these if nulls all over the place. And you saw this when you worked with the linked list in task 3. You're going to have if null, if null, if null. So we're going to check if the root is null. That means we have an empty binary search tree. We saw this in stacks and queues. If top is null, if front is null, if back is null. We saw this to say, okay, the data structure is empty. This is the first node we're going to insert, and this node is going to be the root. And in binary search trees specifically, in our implementation specifically, since we don't have a delete method, that first node that's inserted is going to be the root forever in this implementation. So if the tree is empty, set that new value as the root. Or if it's not empty, we're going to start our recursion. So we're going to set off our recursion starting at the root, and we want a helper method because we want a reference to the node that we're currently considering, the node that we're currently visiting, I often say. We want a reference to that node. With some of our algorithms, specifically with linked list, we got away with not having a helper method with our recursion, if you recall back to linked list, because we used this as a reference to the node that we were visiting, and we would call the next method on the node that we were visiting next. That worked specifically because the method was written in the linked list node class. In those cases, we can get away with that. We can just say this dot next, and then have the recursion go that way and use this. We can't do that because we're outside of the node class, the binary tree node class, so we're going to have to pass a reference. We still want a reference to the node that we're visiting, the current node that we're at, so we're going to create a helper method that has as a parameter whatever we need to get the job done. In this case, I want to know what node I'm currently considering and the value that I want to insert. And we're going to set off the recursion starting at the root node. So helper methods, we've seen quite a few of these by now. Hopefully it's becoming a little familiar. Helper methods when we want to set up recursion, but we don't have the parameters we want in the original method. We only have the value to insert, which is going to be extremely hard to call insert with just the value with recursion and actually get the job done. That's going to be very difficult to set up. So we write a helper method that takes whatever extra information we need. I want a reference to the current node as well. Once we get into our recursion, we're going to call our comparator. We're going to say, comparator, can you compare the value I want to insert with the value at this node? So we're going to compare the value to insert and the value at this node. If this returns true, that means the value I want to insert comes before the value at this node. So if this returns true, it means that the value we're inserting comes before the value at this node, which means we should be looking to the left subtree to insert this value. Everything to the left comes before, everything to the right comes after. If the comparator is saying the value we're adding comes before, we need to be thinking left. If we want to preserve the property of a binary search tree, we need to add this value somewhere to the left. Now, if the left child is null, so if to the left, we're looking to the left and there's nothing there, we found the spot to add this value. We're going to say, well, if your left child is null, you don't have a left child, guess what? You do now. We're going to set that node's left value to a new node containing the value that we're inserting. So we're going to insert the value at that empty reference, that empty node. If the left is not null, recursion. We're going to effectively move to that node by recursively calling this method with the left child as an argument. So we're going to move to the left and continue our search for a place to insert this node. And we're going to keep calling more and more methods. We're going to make recursive calls until we find null. Once we find null, that's where we're going to insert. If the comparator returned false, that means the value we're inserting does not come strictly before this node's value. So it either comes strictly after, or it happens to be a tie. It's a duplicate value. In either case, we're going to break ties to the right. So either case, we're going to go to the right. If the right child is null, we found a home for this node that we're inserting, this value we're inserting. Otherwise, recurse to the right. So we're either moving to the right, moving to the left, moving to the right, based on what the comparator says, or we found a home for our node, and we're going to insert the node as either the left or right child of this node. And recursion is going to go all the way through the tree until it finds a spot for the value to be inserted. So visually, if we want to insert 7 into this tree, we're going to first consider the root node. We're going to start our recursion at the root node. We have a stack frame of the insert helper with the root node as node and 7 is the value to insert. And we're going to check our comparator. We're going to say, hey, comparator, can you compare 7 less than 5? Does the value we're trying to insert come strictly before the value at this node? The comparator is going to say no. It's going to return false, so we're going to move to the right. We move to the right and we do the same thing with 8. We say, hey, comparator, does 7 come before 8? Comparator is going to say, yep, 7 comes before 8, so you need to look to the left. We look to the left, and we find null. So the recursion ends, we find null. That's our base case of our recursion. And we insert the node right there. That's where our node goes, the left child of the node with the value 8. And then all the recursive calls end, return up the call stack, and we give control back to whatever stack frame called the initial find method. Any questions on BST insert? Or BSTs in general? Or anything. I'll take any questions. Y'all gotta have questions. I know you have questions, you just don't ask. Yo. Mm-hmm. Yeah. So what if we want to insert 4 into this tree? Yeah, I can run through it. So since our code is breaking ties to the right, that is going to be the big deciding factor in this one. But let's run through the whole thing. So we're going to start at the root. We're going to ask our comparator, does the value that we are inserting come before the value at this node? It's going to say yes. 4 less than 5, so we go left. Is 4 less than 2 is false, so we go right. And is 4 less than 4 is going to be false again, so we're going to go right again. So because we're breaking ties to the right, which is the way we're using our comparator, we're going to say, if the comparator doesn't say that the value we're inserting is strictly before the value at the node, then we're going to go to the right. So we're breaking ties to the right. So we would get to 4, look to the right, find null, and insert it right here. Sound good? Keep looking at chat. Y'all haven't asked anything in chat in, I think, 2 lectures, so I might stop looking at my phone. Anything else? Is it all making sense? I hope. We are almost halfway there. Can we remove a node this way too? So removal is a bit more complicated. I'm going to, that'll be saved for CSE 250. We can, but we have to be very careful when we remove a node because we have to choose one of the left or right to be able to replace that node and kind of pull one of its subtrees up to that node. So removal does get a little trickier and some we won't tackle in 116. If we were to insert a value like 30, for example, instead of 7, would it become the child of the node containing 14? And would it be the right node? Yes and yes. So if we wanted to add, what was the number? 30? So we would say, is 30 less than 5? False. Is 30 less than 8? False. Is 30 less than 14? False. So we go right, right, right. And then insert it right here to the right of 14. That's where 30 would be added if we were to insert that into this tree. Hey, I'm happy we got questions. All right, let's go through some find. And the reason, I know there are questions. I just don't know exactly what they are. So unless I just guess and just start rambling on about anything, I want to know what the specific confusion is. So find has a very similar structure, but it's going to be just a little bit different. We'll see the differences. So find takes a value and returns true if the value is in the tree or false if the value is not in the tree, as opposed to linked lists that actually returned a reference to the node containing the value. So we have a little bit different setup for our find. We're just going to return the Boolean. So the very first thing looks like insert. We're going to check if the tree is empty. If the tree is empty, I don't even care what the value is we're looking for. It's not in the tree. If the tree is empty, it's not there. We can safely just return false. If the tree is not empty, we're going to call our helper method, which has the same setup, takes a node and the value to find, and we're going to call it on the root node. So we're going to start our search at the root node of the BST. Oh my goodness. Oh, and I got the right slide anyway. I should just drop it to find the slide. Once we get into our helper method, we're going to invoke our comparator again. We're going to ask our comparator, hey, does the value I'm looking for come before the node's value that we're currently visiting? And we're going to make a decision based on that answer. Now, notice when we're inserting, we're very careful to maintain the structure of the binary search tree. We want to make sure everything to the left comes before, everything to the right comes after. I did it backwards. Everything to the left comes before, everything to the right comes after. So each time we checked a node, we said, should this go right or left? And we used our comparator to check that, to make sure we enforce that structure of the binary search tree. So every time we insert, we're enforcing that structure and making sure we maintain that structure. No matter how many values we insert, the way our insert method is structured, it will always still be a BST. The first value is just inserted at the root, and then every node after that follows the algorithm to be able to maintain a binary search tree. When we're doing find, we're on the exact opposite side of that. We're going to depend on that property. We're going to say, look, I got myself a binary search tree, so I know everything to the left comes before and everything to the right comes after. I'm going to leverage that fact to very quickly find if this value is in the tree or not. So we're going to check, does the value I'm looking for come strictly before this node's value? Well, if it does, then I know I need to be looking in the left subtree. I need to go over to the left child and continue my search over there. Because if the value I'm looking for comes strictly before this node's value, it has to be in the left, or else this isn't a BST and everything's broken. So since this is a BST, comes before, has to be in the left, and I can eliminate the entire right subtree. So when I ask the root, hey, root, does the value I'm looking for come before your value? And it says, oh yeah, it sure does. The entire right subtree cannot contain the value I'm looking for. It can't be over there because everything over there is greater than, comes after the value at the root. If the value I'm looking for comes before the value at the root, and by transitivity, all of that stuff in the right cannot be equal to the value I'm looking for if it comes strictly before a value that comes before or equal to everything to the right. So we're going to move to the left. If the left child is null, that means we didn't find what we're looking for. What we're looking for is not in this tree, and we can safely return false all the way up the recursion. Otherwise, we're going to move to the left node and recurse, do the same thing over at the left child. If the comparator returns false for this comparison, we're going to call it again with the same arguments, but in the reverse order. We're going to switch the order and say, okay, the value I'm looking for doesn't come strictly before the value at this node, but does the value at this node come strictly before the value I'm looking for? And if it does, then we know if this value exists. If this value is in the tree, it must be in the right subtree. It cannot be in the left. It has to be in the right if it's in the tree at all. If we move to the right and we find null, we can return false. We can end our search. We know that we didn't find the value. And if there is something to the right, we're going to move to that node through a recursive call. We're going to shift over to that node and continue our search. And then we have one really nice property of our comparators. We talked about two different styles of comparators. One of them returned a positive int, a negative int, or zero, zero being equality. Our comparators only return true or false. So on the surface, it seems like we can't do equality checks with our comparator. But we actually can. We can get the same information that we get out of the int comparator out of our Boolean comparator. The way we do that is call our comparator twice like we are here. So if we call our comparator twice, if we say, is the value I'm looking for, does this value I'm looking for come strictly before the value at this node? And it says no. And then we say, well, does the value at this node come strictly before the value I'm looking for? And it says no. The values must be equivalent. They might not be strictly equivalent. They might be, but they are equivalent according to this comparator, which is what we care about when we're creating a BST. We only care about what the comparator says. So they might not be equal, but they're equal according to the comparator. For example, with the ints, it does mean the values are actually equal. In our example with inserting 4, if we were trying to find 4, we would say, is 4 less than 4? False. Is 4 less than 4? False. Else, okay, these must be the same value. They're the same integer. One's not less than the other, and the other's not less than the other. They have to be the same integer. There's no other choice for integers. But what if the comparator was a string comparator that ignores case, something relevant to your homework? You have a comparator that ignores case and sorts strings alphabetically, and you ask, does this value come before this one? Or reverse them, does this one come before this one? And it says false both times. It does not mean that those strings are equal, but it does mean that they're equivalent according to that comparator, which in that case would mean that they're the same strings, but they might have different mix of upper and lowercase letters. One might be all caps, one might be all lowercase, but they have the same characters aside from the capitalization. So then we would say those are equal because the comparator doesn't care about their relative order. It doesn't matter what order those two strings are in. They'll still be sorted alphabetically because they are the same alphabetically. So if both of these return false, they're the same. And then we can safely return true. We found the value we're looking for. Return true. Visually, let's find 4 in this tree. We're going to start at the root node, and we're going to ask our comparator, does 4 come before 5? In this case, is 4 less than 5? It's going to return true, so we move left. If it's less than the value at this node, then if it's in this tree at all, it has to be in the left subtree. So we're going to move left. Make a recursive call on the left child. We're going to do the same process. Is 4, the value that I'm inserting, less than 2? It's going to return false, so we go to our else if. Switch the order of the arguments. Is 2 less than 4? Does the value at this node come before the value I'm inserting? It's going to say yes, so we're going to move to the right. We move to the right, we do the same thing. Is the value I'm looking for less than the value at this node? No. Is the value at this node less than the value I'm looking for? No. Then they must be the same. According to this comparator in this case being the less than operator, these must be the same. We found the value, and we can return true. We can say, yes, 4 is in this tree. If we did the same thing, say we want to do the same thing, but we want to find the value, let's say 9. I didn't have slides. I realized last lecture I should have slides on a false example when it returns false. Let's try to find 9. We're going to check, is 9 less than 5? It's going to say false. So we check, is 5 less than 9? It's going to say true, so we move to the right. Is 9 less than 8? False. So is 8 less than 9? True, we move right. Is 9 less than 14? True, so we move left. And we find null, so we would return false. 9 is not in this tree. Because if 9 were in this tree, we would have had to have found it in that search. Because every time we made a check, the only things we're eliminating, the only nodes we're eliminating are nodes that cannot possibly be 9. Since 9 isn't less than 5, it can't be in its left subtree. Since 9's not less than 8, it can't be over here. It's not allowed to be over there. It's not allowed to be to the right of 14, because everything to the right of 14 is greater than 14. So if 9 were in this tree, it would be exactly right here. And when we look there, we find null. 9 cannot be in this tree. Even though we only checked 3 nodes, we know that any of the other nodes can't possibly be 9, or else this wouldn't be a binary search tree. So we're leveraging the property of a binary search tree to find values very efficiently. With a binary, I could stop right there actually for a second, if anyone has questions. So regardless of type, the search tree is always going to just add the left or right node depending on what the comparator returns. Search tree is always going to just add a left or right node. Yes. When you insert into a binary search tree, yeah, it's going to look left or right. So if we want to insert, we'll pick on 9 again. If we want to insert 9, it's either going to insert it to the left or right or go down the recursion. So 9 is greater than 5, so we recurse. It's greater than 8, so we have recursion. It's less than 14, and once we find null, that's where we insert the value in the left child of 14. And it's always, yes, it is always according to the comparator. So if we did a decreasing comparator, like we saw last time we saw comparators, this whole tree would just be flipped. It would be the other way around. If we do an in-order traversal on a BST, we will visit the nodes in sorted order according to its comparator. Very important. I only have one slide on this, but very important. In-order traversal will visit the nodes in sorted order. So an in-order traversal makes the left recursive call, visits the node, then makes the right recursive call, which exactly syncs up with the property of a binary search tree. So everything to the left during the left recursive call is less than, then we visit the node, and then we make the right recursive call to visit everything that's greater than. And that recursion goes throughout the entire tree, and the property goes throughout the entire tree. So we go to the left, look at everything that's greater than, less than, go to the left, look at everything that's less than, visit -3, visit 2, then make the right recursive call to visit everything greater than 2 in the subtree, and then return, visit 5, then go to everything that's greater than. For this node, go everything that's less than, then to the node, and then everything that's greater than, and then return. So we're going to visit the nodes in sorted order according to the comparator. Very important. Quite possibly very important for task 6 when you're navigating this tree and creating a list in sorted order. In-order traversal, extremely useful for binary search trees. Pre-order and post-order, not so much. In-order, very, very important, very valuable for binary search trees. Visits every node in sorted order. And let's talk about efficiency a bit. I said the only real reason to use a binary search tree over other methods is efficiency. That's true for like any data structure, by the way. Anyone who says use an array list for absolutely everything, yeah, you can. You can use an array list for absolutely everything. But once you have very large data structures with lots of data you're processing, it's going to be slow. The reason to use better data structures is for efficiency when you have lots and lots of data. If every program you have has like 10 pieces of information, like who cares, just use an array list for everything. Once you get out there in industry and you have 1 million customers all hitting your app, you need the right data structures. So let's talk about efficiency a little bit. We don't talk about it much. A lot of it's for 250. One piece of vocab I mentioned earlier on Monday, but just a reminder, a balanced tree is a tree where each node has about as many descendants in its left subtree. The size of the left subtree is about the same as the size of the right subtree. Did it backwards again. And today's example was what we call fully balanced. It had every node has exactly the same number of elements to the left as it does to the right. Fully balanced tree. If a binary search tree is fully balanced, then we get a lot of efficiency properties out of this. So if, and that's a big if, that's a huge if that the tree is balanced. But if the tree is balanced, the height of the tree, which is the distance, the number of left or rights it takes to get from the root to a null is O of log n, which means our find and insert, which every time we make a recursive call, we do a constant amount of work, and then we make a recursive call which moves down the tree. Every time we do that, we're going, well, I already said it, but we're going down the tree. We're going either left or right, and that's going to have a number of recursive calls, at most O of log of n, which is fast. It's fast. We'll talk about that in the next slide. And we have another sorting algorithm. If you wanted another sorting algorithm that works in n log n time, create a binary search tree and insert all n elements into it. If it's balanced, you'll have an n log n sorting algorithm. So go us, we got another n log n sorting algorithm. And then do an in-order traversal, get all the values in sorted order. Yay. We can't do that necessarily in array lists or linked lists. This should say array lists for Java. But we can maintain this sorted order efficiently. Whenever we add an element, it's still log n. We can't insert elements into an array list or a linked list in faster than O of n. Array lists, if you have to insert in index 0, it takes O of n to shift everything down. For a linked list, if you have to insert in the middle of the linked list, you have to find that node first by going next, 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 and then insert. The binary tree inserting and maintaining sorted order is O of log n. So for example, if you have a leaderboard with 1 million users and you want to maintain that sorted order even as users are setting new high scores, you can update that value with a binary search tree efficiently. So and you can also delete, again, we're not talking about delete, but you can delete in log n time as well if you're careful about it. The efficiency is going to be the height of the tree. So notice in our tree, we have height 3. We have 7 nodes, and we only had to check 3 of them, which is an okay gain. But what if our BST had 1 million nodes? How many checks would we have to get? What's our log n to be able to get to the bottom of this tree? Our worst case find, or our worst case insert. How many times would we have to check? 20. Log n is extremely powerful to be able to get extreme efficiency out of this. Just 20 nodes to be able to store 1 million elements. This is how those 20 questions games works. It's a big tree, and it asks you questions for each node, and then navigates the tree. And with 20 questions, it can store 1 million different things that you can possibly think of.